HR diagrams are a scattergraph of stars. They show the relationship of absolute luminosities versus spectral types and effective temperature. They are not a map of location. They were created in 1910 by Ejnar Hertzsprung and Henry Norris Russell. The relationship shows distinct groupings. The main sequence, which is the general curve of the graph. Giants, bright giants and supergiants lie above the main sequence. White dwarf stars lie below the main sequence, towards the bottom of the graph.
Gas clouds are the very first stage of star formation and can reach up to 300 light years in diameter. They can weigh more than 100,000 suns. These gas clouds are very cold and are between 10 and 20 Kelvin. Gas clouds block visible light, so we must use infrared spectroscopy to find out more about them. 99% of interstellar material is a gas, and 90% of this is hydrogen. 50% of interstellar material occurs in gas clouds. If the gas clouds are not too cold, then individual hydrogen atoms can occur, and if it is over 10,000 Kelvin, then ionized hydrogen can emit light at a wavelength of 656.3 nanometers. Stars begin to form at a certain density as the dense part of the cloud starts to collapse with a mass of 10 to the 4 solar masses. The core fragments into clumps ranging from 10 to 50 solar masses. Gas clouds form and dissociate over a time period of 10 million years. A gas cloud is considered a protostar when the cloud core is independent and has its own gravity and identity. Collapse begins when internal pressure and gravity are not in balance. Infalling gas converts gravitational potential energy to thermal kinetic energy, increasing the pressure and temperature of the protostar. The protostar becomes a source of infrared radiation when the temperature increases to thousands of degrees centigrade. Most of this radiation escapes, and this is called the isothermal phase. It takes 10 million years to form one solar mass. As radiation becomes unable to escape the core, the star becomes a class 0 protostar. More emission comes from the protostar, and it is a class 1. It is equal to the mass of the surrounding envelope. As the surrounding disk becomes smaller, the protostar enters class 2. After the surrounding mass becomes an order of magnitude smaller than the protostar, this is a class 3 or T Tauri star, otherwise known as a pre-main sequence star. Around this star, a protoplanetary disk begins to form and can have a radius of up to 1,000 astronomical units. As the radius decreases, the rotation increases due to the conservation of angular momentum. It is thought that these disks form planetary systems. A star enters its main sequence when it begins to fuse hydrogen. This can have a variety of intermediaries, but often occurs in the form of tritium-deuterium fusion, or proton-proton fusion in stars under 1.5 solar masses. Above this, carbon, nitrogen and oxygen are used as intermediaries in the CNO cycle to form helium. The core of the Sun takes up around 20% of its mass, and it can take 100,000 years for a photon from the core to reach the surface. The rate of fusion must be higher in larger stars to balance the potential gravitational energy, otherwise the star would collapse. So the more mass a star has, the faster its rate of fusion.
A giant star is a star with a substantially larger radius and luminosity than a main sequence star of the same mass and surface temperature. They lie above the main sequence on an HR diagram. Giant stars have radii up to 100 times that of the Sun, and luminosities between 10 and a few thousand times that. Stars still more luminous than giants are referred to as super or hypergiants. A star becomes a giant star after all the hydrogen available for fusion at its core has been expended. The behavior of a post-main sequence star depends on its mass. If the mass is less than 0.25 solar masses, the star will not become a giant star at all. It will fuse hydrogen around its core in a shell-like structure and will become a helium white dwarf. If the mass is greater than 0.25 solar masses, it contracts and the hydrogen starts to fuse a shell around the core. The portion of the star outside the shell expands and cools, but with only a small increase in luminosity, and the star becomes a subgiant. If the mass is less than 0.4 solar masses, the core will never have a high enough temperature to fuse helium in theory, and it will become a helium white dwarf. Our sun will expand to its red giant phase in roughly 5.4 billion years. Super and hypergiant stars are stars that are much larger than giant stars. They can have radii of over 1,000 times that of the Sun. VY Canis Majoris in the constellation Canis Major is such a star. It has a radius of 1,420 plus or minus 120 solar radii. Dwarf star refers to any main sequence star with a luminosity class 5. Red dwarf stars are low-mass main sequence stars. These are the most common type of star in the Milky Way galaxy. They are not easily observed, however, as they have either a late K or M spectral type. This means that they are both cool and have low luminosity. The nearest star to the Sun, Proxima Centauri, is a red dwarf. These stars develop very slowly, having a relatively constant spectral type and luminosity for up to trillions of years. Because of the relatively short age of the universe, late-stage red dwarf stars don't currently exist. Yellow dwarf stars are main sequence dwarf stars, with masses comparable to that of the Sun. A yellow dwarf is a main sequence star of spectral type G. Such a star has about 0.8 to 1.2 solar masses and a surface temperature between 5,300 and 6,000 Kelvin. G-class stars are usually white and vary in color to a light yellow. These stars outshine 90% of the stars in our galaxy, which are mainly orange, red, and white dwarf stars. A G-type star will usually fuse hydrogen for about 10 billion years, until it is exhausted at the center of the star. When this happens, the star becomes a red giant and expands to many times its previous size. Eventually, the giant sheds its layers of gas, becoming a planetary nebula, and the core cools into a compact, dense white dwarf. A blue dwarf is a class of very low-mass stars that increase in temperature as they near the end of their lives. A blue dwarf is a hypothetical class of star that develops from a red dwarf star when it has exhausted the majority of its hydrogen fuel supply. As red dwarf stars fuse hydrogen slowly and are fully convective, allowing a larger portion of the hydrogen fuel to be used, the universe is not yet old enough for any blue dwarf stars to have formed. When a blue dwarf expends the last of its hydrogen, it becomes a white dwarf, which eventually turns into a black dwarf. A black dwarf is a white dwarf that has cooled to the point where it no longer emits visible light. A white dwarf is a star of electron-degenerate matter that is thought to be the final stage in the evolution of stars that are not massive enough to collapse into a neutron star or undergo a supernova. These are stars less massive than 9 solar masses. A white dwarf is thought to be the final stage of stellar evolution for giants whose mass is too low to become a neutron star, which is roughly 97% of the stars in the Milky Way. A white dwarf star's mass is comparable to that of the Sun, however its volume is similar to that of the Earth. If a red giant does not have sufficient mass to generate the required temperatures to fuse carbon, about 1 billion Kelvin, then an inert mass of carbon will develop at its core. After shedding its outer layers, it will leave behind this core, which forms the white dwarf. White dwarf stars do not undergo nuclear fusion. They instead gradually radiate away the residual heat from the red giant phase. Also, they are no longer capped from gravitational collapse by the heat generated from fusion. They are instead supported by electron degeneracy pressure. A brown dwarf is a substellar object that is not massive enough to ever fuse hydrogen, but still massive enough to fuse deuterium. These are less than 0.08 solar masses and more than 13 Jupiter masses.
A planetary nebula is a type of nebula that is made up of gas and plasma. They are named planetary nebula because they look like planets when they are seen through small optical telescopes. Compared to stars, their lifetime is incredibly short, tens of thousands of years compared to billions of years for stars. A planetary nebula is where a normal-sized star in its red giant phase has disposed of its outside layers. Because of this, it shines very brightly and is very hot. The UV radiation emitted ionizes the gas and plasma, which causes the nebula to look like they do. Stars weighing more than 8 solar masses supernova, whereas stars around the Sun's mass become planetary nebula. Due to the lack of hydrogen at the end of a star's life, the outer layers become much cooler due to their expansion. When the core reaches 1 × 10⁶ Kelvin, the helium fuses into carbon and oxygen, therefore the core stops shrinking. Because helium fusions are not very stable, the core starts to shrink and grow very quickly. Because of this, more and more gas moves away from the star and the deeper layers at higher temperatures are sent into space. When the gas reaches 30,000 Kelvin, the cloud is now a planetary nebula. There are around 3,000 planetary nebulae in our galaxy, out of over 2 × 10⁹ stars. They are mostly found in the plane of the Milky Way, and there are more of them closer you get to the centre of the galaxy. Parallax is used to measure how far away they are. Black holes are regions of space from which nothing, including light, can escape. According to Einstein's theory of relativity, it is the result of the curvature of space-time caused by a very dense mass. Around the black hole, there is an area called the event horizon, essentially a point of no return. Black holes are called black holes because they absorb all the light that enters its vicinity. It doesn't reflect anything, like a perfect black surface or body, therefore black holes are invisible to the naked eye. Due to being invisible, black holes are found via their interaction with other matter, for example the spaghettification of other stars and other matter going into a black hole. There are also supermassive black holes which are found in the centre of almost every galaxy in the universe. Even with a supernova, a black hole will form any time there is a lot of matter in a small space, even without enough energy to act against gravity and stop it from collapsing. Black holes emit Hawking radiation, which is black body radiation due to quantum effects near the event horizon. Hawking radiation reduces the mass and energy of the black hole and is known as black hole evaporation. Neutron stars are old stars, usually supergiant stars 20 to 30 times the size of our Sun, compressed into a small area roughly the size of a city. They are basically the collapsed core of a massive star. They spin, or rotate, on their axis at roughly 38,000 revolutions per minute. They emit something called pulsars from their axis. Pulsars are basically beams of electromagnetic radiation. There are an estimated 2,000 known neutron stars in the Milky Way, the majority are radio pulsars. Over time, neutron stars' rotation speed decreases due to the energy radiated from their rotating magnetic fields. As a result, older neutron stars may take several seconds for each revolution, whereas younger stars are hundreds of revolutions per second. Their escape velocity is around 100,000 km per second, where escape velocity is the speed at which the kinetic energy plus the gravitational potential energy of an object is zero. If the star is 5 times or more the mass of the Sun, it makes a black hole. If the star is less than 1.4 times the mass of the Sun, it creates a white dwarf. All of the stars that go supernova are neutron stars. However, some white dwarfs whose mass is nearly 1.4 times the mass of the Sun will sometimes get bigger and collapse into a neutron star. In comparison, on Earth, 1 teaspoon of matter from a neutron star would weigh 6 billion tons. Right. Tell me when.
I'm with a cutie Q. What's your like, homie? What are you into? Ring Rapunzel. I mean, who are you, bitch, new lunch?
If less than 0.25 solar masses, star will not... That is not a... That sentence isn't correct. If it... Super and hypergiant stars are... Wait, what? These are known... What the hell? I can't read from this. I'm having some difficulty reading. Coming this winter, the poor decision.